So what we're going to look at today is we're going to be talking about functions of several variables. Primarily, for our purposes, we're going to look at functions of two variables. Although we could look at functions of 3, 4, 5, how many ever variables we want to. The reason why we're going to look at functions of two variables is because when we add an x and a y and we assume that our function like f is our z, then we can imagine that kind of like working in 3 dimensions. And that's important because that's actually going to help us really think about the graphing of functions of several variables. Now what I'm going to do is I'm actually going to demonstrate some key ideas when we're thinking about functions of several variables to kind of help us to think about the big picture stuff as we start to consider functions in several variables. The other thing that I want you to do is I want you to think about, like, as we work on this particular lecture, is that we're doing something called a qualitative analysis. And a qualitative analysis is not like, we're not looking for answers specifically. What we're looking to do is to understand a function and to understand specific characteristics about that function that help us to understand the behavior of the function. Okay? And that's what makes it qualitative. We're not looking for this is the answer. Instead, what we're looking for is we're looking to understand, basically the overall rough shape of what's happening with the function. What happens as we get bigger in the x direction, bigger in the y direction. What happens in terms of its domain, its range. These are big picture overarching questions that help us give us a rough idea of how the actual function behaves. So what we're going to do now is we're going to look at them qualitatively. So I should say, like, as we get started, what I'm going to do is I'm going to take some specific example functions and I'm going to utilize those in order to demonstrate specific things that we're going to be working on inside of this particular section. Overall, what you want to be able to do is you want to be able, whenever you look at a function of several variables or a function of any kind, you really want to be able to think in these terms, okay? Because it'll help you to better understand the functions, to better work with the functions, understand their derivatives, their integrals, whatever else that we might be doing with them, and to get an overall sense of their behavior, okay? Because oftentimes, whether or not you're doing engineering, you're doing mathematics, you're doing physics, whatever you're doing, what you really want to understand more than anything else is how basically that this function behaves under certain constraints, okay? So let's get started. All right, so we're going to take a look at the function of several variables, and I guess I'm going to start this with a definition. This is just to kind of introduce things. And we're going to get a function of two variables, and that's going to be z equals f of x, y. So we're going to treat z as our dependent variable, and x and y as our independent variables, okay? And the idea here is that we're going to imagine that we have a domain that we're going to call D, and that's going to be basically, if we imagine in a plane, because we're going to see this picture quite a lot. Let's imagine here's my domain, okay? Whatever it is, it's got a certain set of values inside of my domain, okay? And I'm going to map that then onto, and you just have to imagine that here's the number line that represents the z-axis, okay? And so we take something here that has an xy coordinate, and we're going to map it onto somewhere with a z, okay? And that's it, okay? So basically what you're imagining, okay, is you're imagining like, oh, all right, I've got something that's in the xy plane, and it's going to get mapped to something in the z plane. Now what we're going to see is that it's not just that we're going to take like a single point in the xy plane. You could imagine actually that you have, say for example, we take here this circle here, and just imagine that our function, okay, our mapping that has this circle, it maps out here to this, we'll call it z2, okay? So anything that's on this circle, all the values on the circle in there will actually map to whatever z2 is, okay? And that's actually going to be something kind of interesting for us as we work with these functions with several variables, okay? And so we're going to talk about that. We've got this thing over here. This is an xy plane. It represents the overarching, it's the set that we're going to be pulling our domains from, and then our range, okay, are going to be all the values of z that we actually can get something for, all right? And it's going to work very similar to how we work with functions of two variables. Basically, we're going to say, okay, so the range f, or excuse me, the domain, right, is all of the values x, y that give us a real value, right, that define something inside of the z category, and then our range. Okay, the range of f is going to be the set of all real numbers z that has at least one ordered pair belonging to d, stuff that we can get to. all right? And we're going to kind of imagine that this is what we call our mapping. So that's f, that we think this is f as well, all right? And what's going to be kind of cool is that we're going to actually end up getting a lot of cool shapes, right, that we can then map over onto our z-axis. So let's consider this function f of xy equals x squared plus y squared minus 4. Graphically, that's the equivalent of saying z equals the square root of x squared plus y squared minus 4. What we're going to do now is we're going to actually think about, and we're going to consider our domain. The set of all values, okay? These are values x, y, and this is belonging to R2. And just a little quick note about what it means to be R2. These are what we call Cartesian pairs. Cartesian pairs or ordered pairs, okay? And that's what we mean when we write this R2, anything that belongs in that Cartesian plane. We'll get something else called R3, and that's actually like Cartesian triples. Those are real number valued triples, but in this case, we're just got these pairs, x, y. And what I want to do is I'm going to look at this function, okay? And I want to ask myself, do I have restrictions on what x and y can equal? If I have any of those, that's going to end up becoming my domain, okay? So I look at x squared, I look at y squared, and I also look at this square root, right? And we know that when it comes to square roots, we have to have positive values under a square root, okay? In fact, x squared plus y squared minus 4 has to be greater than or equal to 0. All right, well, if that's the case, then what I know is I know that x squared plus y squared, okay, is going to have to be greater than or equal to 4, right? If I add over the 4. But here's the thing about that. The thing about that is that that's not really about x and y, right? Because if we let x equal, say, 0, okay? And that makes the smallest x squared we can have, right? So x squared equals 0. That is the min for x squared. If that's the case, then y, or y squared, okay, would have to be greater than or equal to 4, okay? Or greater than or equal to 2, negative 2, right? Okay? And so that's actually the response that we get. If x squared, okay, was equal to 0, then y squared would have to be greater than or equal to 4. And so what I'm going to do is I'm going to say, okay, well, what does that mean? Well, for example, we can't have 0, 0. So 0, 0 is not actually inside of this domain. So not in the domain. Because if we have 0, 0, that would give me, right? That would give me x squared plus y squared minus 4 equals negative 4. And we'd have an undefined function in the real line. Okay? So we can't have that. What can we have? Like I said, we're going to have this x squared plus y squared has to be greater than or equal to 4. Well, what does that look like? Okay? Well, I'm going to draw this. That's a circle. Well, if we set it equal to 4, excuse me. So x squared plus y squared equals 4, okay, is a circle, radius 2, centered at the origin. So when I draw that out, that's what this is going to look like, right? There's my circle of radius 2, centered at the origin. Remember what I said, that 0, 0 cannot be included inside of that domain? Okay? In fact, we have to have our values greater than or equal to 0. So consequently, all of this area out here, if we kind of just imagine, it's all that stuff. It's all the stuff outside of the circle x squared plus y squared equals 4. So my domain is all of the values x, y, such that x squared plus y squared is greater than or equal to 4, or everything outside of the circle of radius 4 centered at the origin. By the way, you might actually see this written in something called set build notation, and that's going to be the set of all x, y belonging to R2 such that x squared plus y squared is greater than or equal to 4. And that's actually how we write that. And so you're going to see that inside of the writing as well. Okay? And so that's our domain. Does that make sense? Let's see. We want to look at this. We say, okay, well, I need x squared plus y squared minus 4 to be greater than 0. Greater than or equal to 0. So that's what I did. I set it up to be greater than or equal to 0. And then what happened is I get then that x squared plus y squared is greater than or equal to 4, just by adding over the 4 to the other side. I recognize that that's a circle. It's a circle of radius 4 in the xy plane. And I just want to think, well, is that inside of the circle or outside of the circle? Because it's actually an inequality. Take a look, it's actually going to be outside of the circle. So it's outside that circle, that's going to be the entirety of my domain. There's my domain. Okay? Now, by the way, this line here, okay, this line here, we're going to give a name, it's going to have a name in just a little bit. It's actually called a level curve. And that's what happens when z equals 0. We'll talk about that a little bit more in a second, but this kind of like drawing things in this way, where we kind of, you know, eliminate the z, or we set it equal to 0, or set it equal to a value, is going to become a very crucial and handy thing for us to do. Okay? Now, let's take a look at another one. Let's take a look at the range. So again, now if we look at my range, I've got x squared plus y squared minus 4. I'm now looking for my set of z. Okay? The values for f of x y that actually give me where I actually get a value for those. And if I think about this, I know that f of xy, my z value, has to be greater than or equal to 0. Right? It's got to be greater than or equal to 0. It cannot be, in fact, negative, because we can't have a negative under the square root. Next question, is there any set of values that I can't possibly have if we get larger than x squared plus y squared minus 4? I mean, like, is there any top bound? Right? Is there any value? We know that like 0 is the absolute bottom. Is there any value that we can't have that's actually above that? Okay? And the answer is no. Let x be as big as we want. Let y be as big as we want. We're still going to get actual values for z. So what we get here is that this is the range. Okay? That's the range right there. And how we write that in our set builder notation, we got a little curly bracket, and it's going to end up being the set of all z belonging to R. Now that's just a single value, right? Because this is just one variable z, f of xy, even though it looks like maybe it's a couple, it's not. It's just a single variable z, such that z is greater than or equal to 0. And there is our range. You can also utilize f of xy, or we can write the set of all f of xy belonging to R, such that f of xy is greater than or equal to 0. And that's our range. So that gives me my domain, that gives me my range, and that actually starts to set me up for understanding a little bit better what it is that I'm looking at qualitatively for this function. So now let's use some basic ideas that we had in order to talk about these things called a level curve. Okay, so like, let's imagine I have a function f of xy, I've got a number c in the range of f, and I want to understand a level curve of a function of two variables is going to be a value c defined to be the set of points satisfying the equation f of xy equals c. Okay, so let me actually elucidate what exactly that means, okay? We can pick any value c. So c is a constant, all right? Let's select c as a constant. So like, for example, we'll let c equal 0. And what we really want to do is we really want to imagine that this is z equals 0. So for the value z equals 0, what is the function going to look like, right? So, or if z equals 0, right, what is... We're going to call this the trace of the function in the xy plane. Okay? And let me see if I can make that easy to understand. So like, let's say, for example, I take, here's my function, okay? Or here's my xy plane. And I'm going to start out with z equals 0. And so if I plug in z equals 0, I get 0 equals the square root of x squared minus, or x squared plus y squared minus 4. We square both sides, and we get x squared plus y squared minus 4 equals 0 squared, which is 0. Add the 4 over, we get 4. So that's x squared plus y squared equals 4. We actually have already seen that one. So x squared plus y squared equals 4 is a circle of radius 2. Okay? And in your book, they're going to use c equals 2. I'm going to use z equals 2 because that's literally what it is. It's when z equals 2, what does our function look like? Okay, so when z equals 2, right, the graph is the circle, radius 2, okay, and there it is. So we'd actually, it's just, let's imagine this is z equals 2, or c equals 2, like I said. They use that term. So let's imagine instead now, let's, for the sake of ease, let's say, for example, I want to select, we'll select the number 1. So if I let z equal 1 now, okay, so I got z equals 1, I got 1 equals the square root of x squared plus y squared minus 4. So that actually means that x squared plus y squared, right, equals 5. So we're in the square root of 5, and so you kind of just imagine, oh, well, that's just a slightly larger circle. It's a circle of radius square root of 5, which is just a little bit bigger than 2. So there it is, and that's when z equals 2. Okay? Remember how we actually, z equals 5. Pardon me. Or, excuse me, this is z equals 0, and that's z equals 1. Dope. Okay? Z equals 0, and there's z equals 1. So what we're seeing here, what the idea is that, remember how we had that line? We had that number line. Okay? And that number line, this was like the z-axis. You want to imagine that what this inner circle, the one that is x squared plus y squared equals 4, is going to map, it maps to z equals 0. Okay, there's the mapping of f of x, y. And then if I take z equals 1, that z equals 1 is going to map, well, actually what we're thinking about really is that this circle, x squared plus y squared equals 5, is actually in fact going to map to z equals 1. Okay? Do one more, just to give you a sense. If I take z equals 2, okay, so we're going to see what happens if we're going to map to z equals 2. I get x squared plus y squared, and then it's going to square it, so it's going to be 4 plus 4, it's going to equal 8. X squared plus y squared equals 8, so it's just going to be slightly less than 3. Or it's a circle of radius just slightly less than 3, it's the square root of 8. And so that's going to then map to z equals 2. And that's the idea. So what we're getting here is we're getting these things, they're called level curves, and this is called a contour map. Okay? It's called a contour map, and you can kind of imagine, actually you don't need to imagine this, a contour map is something that if you've ever done any, like if you're a Boy Scout or a Girl Scout or have you done any kind of like outdoorsy stuff or utilized a map ever, a contour map, what we oftentimes see is we want to understand elevation on a two-dimensional plane. And so to understand elevation on a two-dimensional plane, what we'll do is we'll actually go in and we'll draw these contours, right, these level curves, and each one of the curves represents a certain rise in elevation. And so what you can kind of imagine is that's what's happening, is that as I go from, if you want to kind of visualize this, as I go from this inner circle out to the outer circle, right, my elevation's going up. It goes from z equals 0 to z equals 1 to z equals 2, right? And so you imagine that I've got this, here I've got this bowl, right? Okay, I can't have anything inside of it, but then as I move upward, right, okay, I'm moving upward on the curve, right, I'm going up on the z-axis, okay? Going up on the z-axis, and that circle is getting larger and larger on the xy plane. Now we've got something called a vertical trace. And a vertical trace is the same exact thing as a level curve, except instead of having our constant be values for z, it'll be a constant, we'll have a constant value for a, or a constant value, value for x, or a constant value for y. And you'll see that in this definition, a vertical trace of the function can be either the set of points that solves the equation f of ay equals z for a given constant, x equals a, or f of x b equals z for a given constant, y equals b. Okay? So now, what we're going to be doing for level traces is a little bit different, although it's going to look pretty much identical, right? It's just we're going to hold a different variable constant. We're going to see that this is going to come in very handy for us when we do partial derivatives, okay? And also when we do integration for multiple functions of multiple variables. The whole idea here is that I can't really, do work in 3 dimensions, or it's kind of difficult. It's much easier to pick something in 2 dimensions. And how I do that is by holding something constant, right? Holding one of my variables constant, pretending like it doesn't change. So that's what we're going to do right here, Okay, so let's imagine once again, what I'm going to do now is I'm going to do one of these. F of ay equals z. Okay, so what that means is this is going to be drawn in the zy plane. All right, so this is that zy plane if you're thinking in 3 dimensions. So now we have the zy plane instead of the xy plane. Why is it zy? We got z and y are the ones that are going to be changing. Okay, remember f of xy is going to equal the square root, or rather, let's make it z. Z is going to equal x squared plus y squared minus 4. That's our function that we've been looking at. And let's say, for example, we'll let x equal 0. So we're going to let x equal 0. And if we let x equal 0, we now get z equals, okay, the square root of y squared minus 4. Okay, so we got the square root of y squared minus 4. All right, and then we'll square, and so z squared is going to equal y squared minus 4. For this function, by the way, what we know, it's a little bit different, okay? Like, this is going to be, right, we've basically got something that's going to look like a hyperbola. We'll see that in just a second. Because what we'll do is we'll create this as y squared minus z squared equals 4. But it's not exactly that because we know that z has to be greater than or equal to 0. So z is going to be only on the positive side. Okay, we'll make this our z and we'll make this our y. Okay, and so we've got this parabola y squared minus 4. Okay, and we've got the value z. Okay, and so basically we'll start here at 2, or we also have this one here at negative 2. Right, we're going to have one at 2 and we'll have one at a negative 2. Nothing in between though, right? Because if y is anywhere between negative 2 and 2, we end up with a function that actually is undefined. And so what we'll get is we'll get this parabola, okay? And it's, pretty standard parabola. Okay? Right? But actually it's not a parabola, it's actually, like I said, it's a hyperbola. Right? 2 parabolas going in separate directions. Okay? These are for the negative values of y, right? So for example, here's for negative 5. Or excuse me, negative 3. Excuse me, actually, pardon me, that's the square root of 5. So just slightly, slightly square root of 5, right, is actually, so it's going to be a little bit larger up there. Something along these lines. So it'll look like that. And this one here as well, it's going to do the same thing. Okay. What's really important is that we've got these hyperbolas, and we've got a hyperbola that only is the positive side of z. Okay. So the positive side of z. And so if we look at this, we're going to say, okay, there's the picture. And this is going to be when x equals 0. Okay, so that's for x equals 0, just like before when we had z equals 0. All right? Instead of this really being, though, like a mapping, where we're imagining a mapping, though, this is just like imagining, well, what does this function look like in that xy plane? Okay? Let's say, for example, instead, we'll let x equal, and we'll say let x equal 1. Okay? So we'll let x equal 1, and so that then is z equals the square root of, and this is going to be 1 plus y squared minus 4. So z is going to equal the square root of y squared minus 3 now. So it's y squared minus 3. And so it's basically, it's the same hyperbola, except we've now moved downward. Okay? We're now at the square root of 3 instead of the square root of 4. Okay? And so that's now going to be our set of points. So actually our domain, right, the domain for this part, the y squared minus 3, right, z equals y squared minus 3, is actually moved inward. Okay? We could actually imagine one more. Let's say, for example, we let x equal 2. If we let x equal 2, then we get z equals the square root, and this is going to be 4. That'll be 4 minus 4, so this is going to be the square root of y squared. So this ends up equaling z equals y. Okay? And so consequently, if we've got the square root of z equals y, that's actually z equals y. So it's going to look like this. Okay? And, in fact, it's also going to end up going out in this direction too. So in this case, right, we're getting... right? And the reason why it's going to be that way is because if y is less than 0, Okay, y squared is still greater than 0. Okay, and so our positive and our negative sides are going to be exactly the same. So basically what's happening here is you're just imagining between, you're just imagining that if we go in between 4 and 1, or 4 and 0, we're going to have that domain kind of like move inward, right? And so you can imagine we've got these hyperbolas, right, until we actually end up with this v in the middle, okay? And those are going to be what our vertical traces look like if we set x equal to a particular value, like x equals 0 in this case. So now what about vertical traces for f of x b equals z? Well, now in this case, we're going to hold y to be constant, and we're going to imagine what happens with in our xz plane. So here's our xz plane. And so in our xz plane, we've got, right, z equals the square root. And let's say, for example, if we let y equal 0, we're going to get x squared, okay? By the way, here's x, here's z. We're going to get x squared minus 4, right? And so we know what that looks like already. It's going to be that half hyperbola that we had before, okay? In fact, it's going to look identical. In fact, the whole thing is actually basically going to look identical, okay? Right? If we imagine, here's what happens if we let b equal 1, here's b equals 0, and then we have this thing here, these straight lines, okay? And that's what happens if you let b equal 2. And there we are. And how they get represented as functions, we get like something like z equals, and this will be x squared minus 3, and that's when y equals 1. And then we have z equals the square root of x squared when y equals 2. Okay? So let's take a look at another example. Let's say, for example, I have f of xy equals xy. Now, when I look at f of xy equals xy, some things that I want to get is, like, first I want to understand what the domain is. And so the domain is actually going to end up being all real numbers. And the reason why that's going to be the case is because I can get anything that I want for x and anything that I want for y. Okay? So we're going to actually say that it's going to be the set of all xy belonging to R2. Okay? R2 being the set of all ordered pairs or Cartesian ordered pairs or duples. Okay? And that's our domain because there's no restrictions on x, there's no restrictions on y. Then also, if we look at this and we ask ourselves, well, what is the range? Okay? Well, the range is also, it's going to be z equal to r. Okay? Or all the z's belonging to r, pardon me. And that's because we can get any value for z either as well. Or maybe we actually rewrite it as f of xy belonging to r. Okay? And again, that just indicates for us that there's no restrictions on our domain in this case. Okay? Now, let's take a look at our level surfaces. Oh, not our level surfaces, but rather our level curves. And let's select, let's say we have c equals, we'll try 2 and negative 1 and 1, okay? And so if I look at this and I set out xy equals 2, what I get is I get y equals 2 over x, okay? And that's my level curve there. If I set c equal to negative 1, I'm going to get xy equals negative 1. And that's going to give me y equals negative 1 over x. And if I go with, okay, and so here's z equals 2, z equals negative 1, z equals 1. Then I get xy equals 1, and that's going to give me y equals 1 over x, just with a little bit of algebra. Now when I draw my level curves, okay, again, this is going to be in the xy plane, okay? And so, say for example, I take, well, essentially, what I got here is I'm going to have an asymptote at 0, okay? And essentially, that's going to kind of look like the one that we have for 1. So this is z equals 1, for example, z equals 1. It's just approximate. If I take negative 1, what I'm going to get is I'm going to get something that looks like this. Okay, so here's z equals negative 1. And we'll get, it'll be mirrored up here in the second quadrant as well. Z equals negative 1. And if I take 2, what I'm going to get, I mean, essentially it's going to have the same basic asymptote, but what we're going to get is a little bit further out. Okay, and so there's z equals 2. And I'm going to get it similarly along the other side as well. Okay? And basically, for these ones, I pretty much, kind of just visualized what the graph of y equals 1 over x equals, or 2 over x. And so, again, that's z equals 2. Okay? If we wanted to do negative 2, by the way, that's negative 1, we can imagine that it's pretty much going to look somewhat similarly, just be mirrored from positive 2. Okay? And so those are going to end up being our level curves. Let's take a look at these vertical traces. So in this case, we're going to be in the zy axis, or the zy plane. Okay? So we'll let y be our independent variable, and z be our independent variable. And if I take a now is just a value for x that we'll choose. So we'll let a equal, say for example, 1. So if I let a equal 1, what happens? I get z equals y. That's that line right there. If I let a equal 2, I get z equals 2y. Right? And it ends up being that line right there. Okay? And so here's my trace. This is when x equals 1. Here's x equals 2. If I say, for example, I let a equal 0, okay, then I get z equals 0. Okay? And so, in fact, z equals 0 is going to end up just being this y-axis. Be careful. Notice that, it's not the x-axis in this case because we have a different coordinate plane. And that's basically what our vertical traces are. And in this case, our vertical traces are going to be pretty much identical if we're looking at the, we'll call this yz plane, pardon me, if we're looking at the xz plane as well. Okay? Because basically you're going to get a constant value for y in this case, so you'll get z equals some constant value times x. Now, if I think about it, what does this mean? Okay? So if I kind of imagine here what's happening on my surface, right, is that as we kind of move up in the xy plane, what I'm getting is right, that z equals 1, we're getting, as I get closer and closer, right, I can get closer and closer and closer, and these are values of z that are getting smaller and smaller, okay? Until you finally get to, say, for example, z equals 0, and z equals 0 is going to end up being either this x-axis or the y-axis. It's either x equals 0 or y equals 0. So you're kind of imagining like you've got these curves, and the z-axis, as we're moving upward, we're moving up. As we're moving away from the x and y axis, we're moving upward on the z-axis. Okay? So basically, if you kind of imagine in 3 dimensions, let me kind of draw this, see if we can kind of draw this. Okay, here we go. I hope I can do this. All right, so here's quadrant 1, and what we've got here is we're kind of imagining that you're getting something that kind of looks like it's expanding outwards as you go upward, right? You're getting kind of like a cone or a funnel shape, okay? As we kind of move upward. Hard to do by hand, right? But it's kind of does one of these things, okay? Because those are, and actually it goes outward. Pardon me, goes outward. Goes outward away, outward away, outward away, right? Just in that first quadrant, if you kind of imagine what's happening there. And it does that in each and every one of the quadrants, right? You're getting these things that have, essentially, the curves have an asymptote as you approach 0, right? Okay? But they're getting closer and closer and closer to, that line. Okay? Yeah. So, kind of interesting, I guess. At least as I'm thinking about it, or as I'm visualizing it. Okay? As you can tell, the fact that I can't really draw it very well kind of lends to the reasons why we do things like vertical traces and level curves. Okay? So let's kind of go through this, just a reminder of what we're going to be doing. When we look at our domain, what we're going to imagine is we're going to imagine restrictions on our values x and y. Okay? In this case, there are no restrictions. No square roots, no dividing by 0, no issues there that we've got to actually deal with. Okay? And so that's why we have this duple. Our xy's are all of R2. We can choose anything for R2 that we want. And what is our range? Well, it's going to be anything in R. Our level curves, if you remember, we're going to select a value for z, right, our f of x, y, and then we're going to basically draw this as a function, write it as a function of y, and then we can draw those curves on the xy plane. And what that's supposed to do is it's supposed to give us a sense of kind of the overall shape of the figure. Okay? It takes a little practice, kind of have to think through it. It's a little hard. It's a little hard to visualize, I have to say. And then we have our vertical traces, okay? And with our vertical traces, right, we're going to select a value either for x or for y. We're going to keep a constant value for x or y. And then we're going to say, okay, well, given that I have a constant value for x and y, okay, what do those pictures look? What do those look like? In this case, we've just got a bunch of straight lines with different slopes. Okay, and so essentially that kind of is everything that we want to think about as we're looking, or not everything, but it's a good chunk of what we want to think about as we first encounter a function of several variables.